Okay, so for this lecture, we are going to concentrate on naming inorganic compounds, all right? Inorganic compounds are going to be broken up specifically into three main categories. Ionic compounds, molecular compounds, and then acids. And acids are going to be a type of molecular compound, but because they're named differently from other molecular compounds, we're going to give them their own little group. All right, so you can refer back to your notes packet for the naming section for the presentation part of this lecture. Okay. All right, so when we talk about ionic compounds, we're talking about things that are composed of metals and nonmetals. That is going to be the defining characteristic for you of an ionic compound. Okay, and here are some examples. These ionic compounds have just single cations and anions, as well as cations and polyatomic anions. Okay, these are some of the bigger things that we're recognizing in these later compound examples. But they're all examples of ionic compounds. They're composed of metals and nonmetals. We have two naming systems that we should be familiar with when we're looking at ionic compounds. We have the system that it's called the common naming system or the older naming system. And these names are names that used to make more sense and they used to be more used than they are now. They don't tell us a lot of information about the chemical structure of the compounds that are involved. They're just names that you need to be familiar with because they've been used for such a long period of time. And so they're still used a little bit today, even though they don't make maybe the most sense structurally, okay? The naming system that we're going to learn is the systematic naming system. And that is going to be based on a list of rules, and we're going to be able to assign names to compounds based just on their chemical structure. All right. There are two types of ionic compounds we're going to look at in particular, type 1 and type 2 ionic compounds. The difference between them is going to be whether or not the metal in that compound has a charge that can change from compound to compound or one that remains constant. Okay, so a type 1 compound has a metal whose charge will never change. The ion is always going to have the same charge in every form. Okay, the charges of the main group elements are usually the ones that don't change, and these charges can be predicted right from the group number. The second type of ionic compound, the type 2 ionic compound, has a metal that might change, that will change, depending on the compound that you're looking at. The charge of a type 2 metal in a type 2 ionic compound has to be specified every single time, okay? Because the charge can't be predicted based on the group number, like the type 1 compounds. So these are the charges specifically that you need to be familiar with of metals whose charge never changes, all right? So these are really the only metals that you are going to consider type 1 metals, all right? These are the ones that you will never have to specify. They will always follow the charges that are assigned to them on this periodic table. We're going to name these ionic compounds by first looking at the metal, figuring out what metal it is, and naming that metal. Okay, and that metal is also going to be the cation because it will be positively charged. And then we'll take the nonmetal base name or root, and we will add an IDE ending to it. Okay, so anything that is an anion, anything that's a nonmetal, we can find the root of that really by looking at the front part of that element name. So the base name of chlorine would be chlor, sulfur would be sulf, et cetera, okay? And here are a list of common nonmetals and their corresponding anion forms. So you'll notice that fluorine becomes fluoride. Chlorine becomes chloride. Okay, and it goes all the way down to phosphorus. So phos is the base name, and then we add the IDE ending, so it's phosphide. All right. So here's an example. We have the name for KCl. We would look first at the cation and recognize that it's potassium and write down the name of the metal. Then for the anion, we know that it's chlorine, so we'll take the base name for that, which is chlor, and add the IDE ending. So it would be potassium chloride. For CaO, we start by recognizing the calcium, then recognizing that this is oxygen attached to it, and the base name for oxygen is just OX. So this would be calcium oxide. In both of these cases, these are type 1 metals. If we go back to our chart, see we have calcium here and we have potassium here. These are both type 1 metals. So potassium will always have a +1 charge. Calcium will always have a +2 charge. That means when we're naming both of these compounds, we do not need to include the charge in the name because the charge never changes. Okay, so let's look at these examples. I'm going to switch over to my whiteboard so that we can do these examples out. Okay, so the first example, we have CaBr2. Okay, we're going to recognize that Ca is calcium. We're going to recognize that that Br is bromine. We're going to keep the base name and we're going to replace the ending with IDE. So this is going to be calcium bromide. Okay. For the second one, we have Ag3N. Again, we have a metal that's charge never changes. And we know that that Ag is silver. Here we have nitrogen. That's the base for nitrogen. So we'll get rid of the rest and replace it with IDE, silver nitride. Okay, now if we want to write a formula for something from a name, so we have rubidium sulfide. Okay, I need to recognize the ions that form for each of these. Okay, so I have to look on the periodic table, and first I have to find rubidium and write it in its cation form. Okay, and then I have to look up sulfur and I have to write it in its anion form. And then I have to ask myself, how many rubidiums am I going to need to balance out the charge of this sulfur, right? Because for an ionic compound to form, we have to have charge neutrality. So I'm going to need 2 rubidiums for every 1 sulfur to form a neutral compound. So my formula here will be Rb2s. Okay. If we look at the example on the next slide, it asks us to give all of the compounds containing no other ions than K+, Ca2+, Cl-, and S2-, and then to name each compound. Okay. Let me just show you this slide real quick. That's the one that we're doing right now. Okay. So the first thing is to recognize that the cations are going to be reacting with the anions. Okay, we can't have a cation react with another cation. That's not how it works. So the potassium can react with the chlorine and the sulfur, and the calcium can react with the chlorine and the sulfur. All right, so the first thing we can do is write out those formulas. So we have the potassium and a chlorine, a potassium, a sulfur, calcium, and a chlorine, and then a calcium and a sulfur. Okay, and again, we're forming electrically neutral compounds. So we need one potassium and one chlorine. For the potassium and the sulfur has a -2 charge. Potassium is only +1. So I'm going to need 2 potassiums for every sulfur. My calcium is +2. My chlorine is -1. So I'm going to need 2 chlorines to balance out that charge. And then my calcium is +2 and my sulfur is -2. So they will combine in a 1-to-1 ratio. All right, now if I want to name these, calcium and potassium, like we discussed before, are both type 1 metals. And they're going to form type 1 ionic compounds. So we'll name the metal first. And then the nonmetal root, which is chlor, and the IDE ending. Same thing here, we're going to start with our potassium metal. Then we'll take our nonmetal root and the IDE ending. Calcium, our nonmetal root, and then an IDE ending. Okay, and then one more time, calcium, our nonmetal root, and our IDE ending. And again, notice that there are no parentheses with charges in the middle because all of these are type 1 metals. Okay, now we're going to do the next example. We're going to look at this one now. We'll give the formulas for each of these combinations. And then we're going to look at the issue that we run into, naming 5B versus 5A. Okay, this is going to be the real issue that we run into. So for 5A, we are going to look at the compound where barium is going to form with iodine, and then barium with nitrogen. Okay, so the barium and the iodine are going to form, for every 1 barium, we're going to need 2 iodines to balance out that charge. For the barium and the nitrogen, I have a +2 charge here, and I have a -3 charge here. Okay, so it's not as easy as it was in this first example to say, well, 2 -1 charges will counter a +2 charge, because here I have +2 and -3. So I have to look for a common number between the two of them. Okay, and the lowest common multiple, I guess we could say, between 2 and 3 is the number 6. Okay, so if I have 3 bariums, let's say, my total barium charge would be +6. If I have 2 nitrogens, my total negative charge would be -6. And now I have a +6 charge reacting with a -6 charge, and I have charge neutrality. Okay, so I'm going to transfer these little multipliers into my formula. So I'm going to have 3 bariums, which will be Ba3, and 2 nitrogens. Okay, how am I going to name these? Barium is going to be a type 1 metal, so I don't need to indicate the charge. This will just be barium iodide. This will just be barium nitride. Okay, easy enough. Now we're going to look at 5B, and we run into a bit of an issue. Not with making the formulas, we can do that. We have Fe2 plus and O2 minus. Then we have Fe3 plus and O2 minus. Okay, so if these two things are going to combine, the +2 charge and the -2 charge will balance each other out. So I only need one of each to get a charge neutral compound. For Fe3 plus and O2 minus, I'm basically in the same situation as I was up here. So I'm going to need 2 irons to give me a +6 charge. And I'm going to need 3 oxygens to give me a -6 charge, so I can have charge neutrality. So my formula will be Fe2O3. Right? Now, if I was going to name these using the system that we've already been using, I would just have iron, and then the base name for my anion and an IDE ending. The problem is that if I use that same system, I end up with the same name for both of these compounds, and both of these compounds represent different formulas. Okay, that's because iron is a type 2 metal. And if you have a type 2 metal, you're going to end up with different combinations of elements. Okay, and those combinations are different based on the charges of the cations that make up the compounds. All right, so that's what we're going to look at in this next section. Okay, how do we name type 2 metals? And the only real difference between naming a type 1 metal and a type 2 metal is that we're going to use a set of parentheses between our cation name and our anion name, and we're going to indicate the charge of the metal in those parentheses. Okay? All right, so in our last example, we had 2 names. Both of the names were iron oxide. Now, we could differentiate between the 2 compound formulas if instead of just writing iron oxide, we wrote iron 2 oxide next to the Fe2 plus compound, and we wrote iron 3 oxide for the Fe3 plus compound. This would have told us the formulas of both of the compounds that we were looking at. Okay, and let me show you what I mean. So we're going to look at iron 2 and iron 3 oxide. Okay, say that I had this written down versus this. Sorry, this is supposed to be a parentheses. My parentheses and my Roman numerals kind of look the same. Okay, so say I have these 2 compounds. When the type 2 metals are written with their charges in the parentheses in the middle, now we can build the correct formulas from the names. Okay, because now I can look at this and I know that if I have an iron 2 ion, that's Fe2 plus. And oxide is going to be the oxygen anion, and that will always be O2 minus. So now I know that the formula for iron 2 oxide comes from these 2 ions, which means that the actual formula has to be FeO, because Fe2 plus and O2 minus are going to combine in a 1-to-1 ratio. Over here for the iron 3 oxide, I have Fe3 plus and O2 minus. I know that the iron 3 and the oxygen ion are going to combine in a 2:3 ratio, right? I'm going to need 2 of these for every 3 of these to have charge neutrality. So I know that the formula for iron 3 oxide would have to be Fe2O3. Okay. Go back to our slide. So these are some examples. Okay. We have examples here using iron and copper. If we have Fe and SO4 combining in a 1:1 ratio, you know that you have a 2+ iron ion because the sulfate polyatomic ion is a -2 charge. If you have Fe2SO4 3, you know you must have the iron 3+ ion because you needed only 2 irons to balance out 3 sulfate ions. Okay, and you can look at the copper and the oxygen down here to come to the same conclusion. If the formula is Cu2O, that means that you needed 2 coppers to counteract the oxygen charge. So every copper must have had a +1 charge. If the formula of the compound is CuO, then the copper must have had a +2 charge for the oxygen's -2 charge to be counteracted. This is a generic layout of your main group versus your transition metals. Okay, the main group are in yellow, the main groups are in yellow. So it's your 2 end columns on the left, and then your 1, 2, 3, 4, 5, 6 columns on the right. Okay, and the blue rectangle in the middle are your transition metals. Now, the general rule is that main group charges don't change and transition charges change. I showed you that previous periodic table example though that has specific charge breakdown. So you can see that there are some exceptions to this general rule, and you do need to know those exceptions. All right, so naming these actual compounds. This is how we're going to do it. Okay, we're going to take the name of the cation like we were doing previously, and we're going to follow that cation name by a Roman numeral in parentheses. And the number in the parentheses is going to indicate the charge of the metal. It does not indicate how many atoms that you have. It indicates the charge of your metal. So when you see an iron 2 like this, that doesn't mean you have 2 irons. It means that your iron is a +2 charge. Iron 3 means that your iron is a +3 charge. Okay, and this is the basic formula, or your basic format for writing out the name. And you see the only difference between this and the type 1 binary ionic compound is this middle part here, where we're going to include the charge of the cation. Okay, so here we're going to work through the steps for naming CRBr3. Okay, before you can name a type 2 ionic compound, you need to figure out what the charge of the metal is. That is step 1. Okay, so you know that it's a neutral compound. You don't see any charge anywhere around this. So you know that the charges of the chromium and the 3 bromines are going to cancel each other out. Okay, you also know that bromine's charge is a -1. And that's because it is in the 7th column on the periodic table, right? Group 7. There are 3 bromines. So that means the total contribution from all the bromines is a -3. So the chromium charge, there's only 1 chromium. That charge has to counteract that -3 charge from the bromines. That means that the chromium has to have a +3 charge. That means that we know the chromium cation is called chromium 3. And now we can name it, right? We'll have the chromium 3, and then afterwards, the base name of the anion and the IDE ending. So it's chromium 3 bromide. Okay, Now, these are a list of the older naming systems, and these are the ones that you need to be familiar with. Okay. The reason why we ask you to be familiar with these specific older naming conventions is because these are the ones that you're going to still see used in a chemistry lab. All right, so you have to be familiar with the common older naming systems so that you don't run into a situation in lab work where you're not sure what something means because it happens to be a reagent bottle that's using the older naming system. All right. Now, you're going to notice that in each of these pairs, right, we're not always dealing with the same charge in all these examples, right? We have charges of +2 and +3, charges of +1 and +2, +2 and +4, et cetera, et cetera. What is true for all of these examples, though, what matches for all of them, is that we have one ion that has a smaller positive charge than the other ion. The ion that has the smaller positive charge is always going to have the OUS ending. And the ion with the larger positive charge is going to have the IC ending. Okay? That's a relationship that you need to pull out of this table. The other thing that you need to pull out of this table are the different name formats of these things, okay? So iron is, it changes basically into ferrous or ferric. Okay, it's not like ironous or ionic, like how chromium is just chromous or chromic. Iron is an example of an older root name that's being used here. The same is true for copper, for tin, and for lead. And you have to know these names, okay? So let's look at some examples of naming type 2 ionic compounds. I'm going to do these on the whiteboard. So we have PbCl4. So the first thing that we have to do is recognize that this is a type 2 compound. Okay. Once we recognize that it's a type 2 compound, then we're going to find the charge of that cation. The charge that's not going to change is the contribution from the chlorine. So we have Cl -1, and there are 4 of them, which means the total charge contribution from the chlorine is -4. That means the charge of the lead has to be +4, so we can counteract this -4. Okay, that means that this ion is the lead-4 ion. And the name of this compound will be lead-4 chloride. Okay. The second example is FeS. S has a -2 charge. There's only one of them. There's only one iron, so this must be the Fe2+ ion. That means that the formula, or the name for this rather, is iron 2 sulfide. Or if we want to just have an example of going back to our older naming system, we could also call this ferrous sulfide. Okay, ferrous sulfide, because it comes from the iron 2 ion. All right. And actually, we could do the same thing for lead-4 chloride. The older naming system name for this would be plumbic chloride. Okay, it has the IC ending because we're looking at the lead-4 ion. Okay. The final question was write the formula for ruthenium 4 oxide. So to write out the formula for ruthenium 4 oxide, we have to pull out the charges of the anion and the cation. Okay, in this case, this is easy because they're telling us the charge on the ruthenium. And the oxide is O2 minus. Okay, so if we look at this, we know we need to make a neutral or an electrically neutral compound. That means that we're going to need 2 oxygens to counteract the positive 4 charge of the ruthenium. So we'll need 1 ruthenium and we'll need 2 oxygens. So that's the formula that we would get. Okay. The next type of ion we have to look at is what's called a polyatomic ion. Okay, and a polyatomic ion is a group of nonmetals that are covalently bound together. But when they are covalently bound together, they end up with a charge attached to them as a group. Okay. You are going to use a polyatomic ion like any other ion. Okay, and polyatomic ions will never break up into their separate components if you're going to like dissolve them in solution or something like that. They stay as a unit. Okay, so this example that we're looking at in this 4th bullet, NaNO2. I'm going to bring you back over to my whiteboard for a second. Okay, when you look at this compound, what you should be able to do is first of all recognize the metal component, and the metal component's always going to be at the beginning. Okay, and it's always going to be one type of element. So here we have our sodium. Okay, so we know that the rest of this must be sticking together. Okay, and it turns out that NO2 minus 1 is a polyatomic ion, and it's called the nitrite ion. Okay, now if you put sodium nitrite into solution, what happens to it is this. You have your NaNO2, and now you're going to put it into some water, and the sodium ions are going to break apart and stick together. And then your nitrite ions are going to break apart from the sodium, but they're still going to stick together as a group. Okay. It's very important to recognize the fact that your polyatomic ions stay together as that group. You usually can recognize that you're looking at some kind of polyatomic ion when you see the name of the compound end in ITE or ATE. If you look at your polyatomic ion list, you'll see that most of the names end in ITE or ATE. And at least when you're first learning this, you know, you're always looking for a way to recognize what a recognize a polyatomic ion just from the name of the compound. It's one of your conceptual connection questions, asking you to pick out the group 1 or the type 1 metal. All right, but here is our polyatomic ion list. You do need to know everything that's on this table. You have to be able to use all of these polyatomic ions when you're either making formulas from names or names from formulas. We're also going to be balancing chemical equations later on, and you have to be able to, you know, look at an equation in words and convert all of those chemical names into actual formulas that you can balance. So it's important that you know the names of each of these things, the formulas, and you have the correct charges associated with the formulas. All right. It looks more overwhelming than it is, though, because if you take a look at a lot of these, they differ by 1 or 2 components. Okay, they come in like sets. So you see we have carbonate here and we have hydrogen carbonate right below it. The difference between the hydrogen carbonate and the carbonate is going to be literally the addition of a hydrogen ion. Okay, but otherwise these look very similar. We have nitrite and nitrate. Those differ by 1 oxygen. We have chromate and dichromate. They're both chromium and oxygen. There's just a slight difference between the numbers of chromiums and oxygens. All right, so you see this trend continue throughout the table. All right, and we're going to talk actually a little bit more about some of these oxyanion series in another slide or two. Okay, there it is. So we call something an oxyanion when it contains oxygen. Hopefully makes sense. But the names of these oxyanions are dependent on the number of oxygens that are attached to the other nonmetal in that ion. Okay, and there are 2 types of oxyanion series. Just go off of my whiteboard for a minute. So you have your oxyanions, and you have 2 types of series of oxyanions. You have these 2 ion series, or you have 4 ion series. Okay, and you're going to notice that in the 2 ion series, the only difference between the components is the addition of or removal of 1 oxygen. All right, so our first example on the slide you're looking at is NO3 minus, and the other possible ion here is NO2 minus. So we have 3 oxygens and we have 2 oxygens. Okay, the component in the series that has more oxygens is going to have an ending that ends in ATE. So this polyatomic ion is called nitrate. The version with 1 less oxygen will have an ITE ending. So it's called nitrite. If we look at the other example with sulfur, our 2 members of the series are SO4 2 minus and SO3 2 minus. Notice the charges don't change in these. The only thing that changes between each member of the series is one has more oxygen and one has less oxygen. The one that has more oxygen is going to have the ATE ending, so that will be sulfate. The one that has less oxygen will have the ITE ending. All right, so that's the 2 ion series. If we have a series with 4 ions in it, we have to add a little more differentiation to keep everything separated. Okay, we're still going to use the ATE and ITE convention, but we're going to add an extra prefix to the thing with the most oxygen and the thing with the least oxygen. All right, so let's look at the chlorine series. It's like the one that's on your slide. So the thing with the most oxygen is ClO4 minus. Then there's ClO3 minus, ClO2 minus, and ClO minus, right? So see these 2 middle pieces of the series? We're going to name these the same way that we named our last examples. The thing with more oxygen will have an ATE ending. The thing with less oxygen will have an ITE ending. right? Now, the thing with the most oxygen is going to have an extra prefix added on to this term, okay? And that extra prefix for the most oxygen is PER, okay? And that's because the prefix PER means more than, all right? So it has more oxygen than chlorate. It's perchlorate. Then our last member of the series, which has the least oxygen, we're going to add a prefix to our chlorite term. And the prefix that we're going to add is hypo. And that's because hypo means less than. So it has less oxygen than chlorite. Okay, so this is going to be the most oxygen. This is going to be the least oxygen, and that's the order that it goes. So you could see this with chlorine, with bromine, with iodine. All of these are potential oxyanion series that contain 4 ions in them. All right. So let's look at some examples. I'm going to go back to my whiteboard, but I just wanted you to see which slide we're going to do examples of. All right. Now, the first thing you have to ask yourself in each of these examples is, am I looking at a type 1 metal or a type 2 metal? Because it makes a difference. Okay, so we have Li2, Cr2, O7. Right, now I'm going to look at this right away and say, all right, that is lithium. Lithium is a group 1 metal, and it is a type 1 metal, right? So I can just name it as lithium. I don't need to indicate the charge of a type 1 metal. Then I have to recognize what the name of this polyatomic ion is, and that is the dichromate ion. So this is lithium dichromate. Okay, my next example is SN ClO3 2. Now this is a little bit trickier because I see that I have tin over here, and I know that tin is a type 2 metal. So I have to know what the charge of tin is before I can name this compound. Okay, to find the charge of tin, I'm going to have to look at my polyatomic ion, right? This is the ClO3 minus 1 ion, which is called chlorate. Okay, I know that the chlorate has a -1 charge and that there are 2 of them. So that means that the total charge contribution from my anion is -2. That means the charge on my tin has to be a +2. So this must be tin 2 chlorate. Okay. Now the last question is, write the formula for cobalt 2 phosphate. Okay, so I'm going to have to pull the charges out of the name and then see how they combine to make a neutral compound. So cobalt 2 means that I have CO2 plus. Phosphate is PO4 3 minus. Okay, so if I look at the +2 and the -3 charge, I see that I'm going to need 3 cobalts to get a +6 and 2 phosphates to get a -6 and have an electrically neutral compound. Okay, so that's what has to be reflected in my formula. So I have 3 cobalts, and I'm going to have 2 phosphates. I'm going to put the entire polyatomic ion in parentheses so that this 2 indicates that I have 2 of these whole groups. Okay, I don't want to just put a 2 afterwards and then get it confused with, you know, the subscript that's attached to the oxygen here. All right, now if we look at the next slide, we have a lot of examples here. Okay, so turn to that slide. I'm going to write down the formulas for each of these examples. Okay, so A is iron 3 carbonate. That means that I have an Fe3 plus ion, and carbonate is CO3 2 minus. Okay, so how is that going to combine? That means I'm going to need 2 irons and 3 carbonates. Okay, and then I'll have an electrically neutral compound. Okay, calcium sulfate. Calcium is 2 plus, sulfate is 2 minus. These will combine in a 1-to-1 ratio. Copper 1 sulfide. That's copper plus 1. Sulfur is -2. So I'm going to need 2 coppers to combine with 1 sulfur to make an electrically neutral compound. Okay, lead 4 oxide. That's Pb 4 plus. And oxygen is 2 minus. That means I'm going to need 2 oxygens to combine with 1 lead to be electrically neutral. Okay, cobalt 2 acetate. Cobalt 2 plus. And then my acetate ion, C2H3O2 minus 1. So I'm going to need 2 of these ions to counteract the charge of my cobalt. So 1 cobalt, and then I'm going to have parentheses so I can get this whole group in there. Okay. And we'll have 2 of those. All right, potassium permanganate. K will be +1, and the permanganate ion is MnO4 minus 1. Those will combine in a 1-to-1 ratio. So KMnO4. Okay, and then we'll have sodium hydrogen carbonate. Sodium will be +1. Your hydrogen carbonate ion is HCO3 minus 1. So these will combine also in a 1-to-1 ratio. Okay. All right, now we're going to look at the reverse type of example, and I'll do these ones as well, where we have the formulas for ionic compounds, and we're going to pull the names from the formulas. All right. Now the big key here is going to be remembering that your first step has to be deciding whether you have a type 1 or type 2 compound. Okay, so for 5A, we have K2Cr2O7. Potassium is a type 1 compound, so we don't have to worry about making its charge clear. It's always +1. So we can just name the metal and name the accompanying anion. And in this case, that's the dichromate ion. For 5B, we have to figure out what the charge of the copper is. So we have Cu3PO4 2. Okay, we know that the charge on the phosphate is a -3. We know that there are 2 of them, which means that the total charge from the phosphate is going to be a -6. We know that there are 3 coppers. So we know that if each copper has a +2 charge, that would give us a total positive charge of 6, which would balance out our total negative charge of 6. So the charge on the copper must be a +2, okay, based on the fact that there are 3 of them. And 3 times +2 is +6, okay? So now we're going to name it using that charge. So this would be copper 2, because remember, what goes in the parentheses is the charge, not the number of coppers. Copper 2 phosphate. Okay, our next example, we're going to do something similar. We have CONO3, 2. We know that each NO3 -1, each nitrate has a -1 charge. There are 2 of them, which means the total anion charge is -2. That means that this cobalt has to be a +2 charge. So the name has to be cobalt 2 nitrate. Okay. Now our next example is a type 1 compound, so we don't have to worry about the charge. We can just name it based on the metal and the corresponding anion. So it's going to have barium, and then it will be acetate, barium acetate. No indication of charge for a type 1 metal. 5e is similar. We have strontium. Strontium is also a type 1. It's attached to the hydroxide ion, so it will be strontium hydroxide. No indication of charge for this type 1 metal either. Okay, then we have 5F, Fe2, SO3, 3. Okay, we can recognize the sulfite ion here. You know that the sulfite ion has a -2 charge, and there are 3 of them, which means that we have a -6 charge total. We have 2 irons. That means that each iron must have a +3 charge if it's going to counteract this -6, right? So we have 2 irons. Each one has to have a +3 charge. That will give us the +6 that we need to balance out the -6. So once we know the charge on the iron, then we can name it. Okay. Now the last thing we have to look at in terms of ionic compounds are the hydrated compounds. Okay, and the hydrated compounds are going to work exactly like any other ionic compound. The only difference is that we're going to add the number of water molecules attached to that ionic compound at the end of the formula and at the end of the name. Okay, so when you see this dot after an ionic compound and it's followed by a certain number of water molecules, these are called waters of hydration. Okay, so we have this example here, MgSO4, and then a dot, and then 7 H2Os. So we're going to name this ionic compound the same way we name any other ionic compound. So it's magnesium sulfate. Then we're going to take a breath, put a space in there, and then we're going to indicate how many waters are attached. Okay, so there's 7 waters here. That's where that hepta comes from. And then the word hydrate, and hydrate means water. So we're saying that there's magnesium sulfate and 7 waters. Okay, these are the prefixes that you need to know for the hydrated compounds. Luckily, they're the same prefixes that we're going to use in the molecular naming convention. So you get to use them more than once when you're memorizing them. All right, and these are just some examples of what these names would look like. I'm going to stop this and write some of them out. Okay. Because like when you see the words, it's not always the same as if you're starting from scratch and you like have to do it yourself. Okay, so say you have this, and then you have a dot, and then a half H2O. Okay, and you were just told to name this thing. You're going to start just by naming the first part. Okay, so you're like, all right, this is a type 1 metal. That's a polyatomic ion. So that's calcium sulfate. So after you name the ionic compound part, that's when you deal with this part. And so you say, all right, I have half of a water molecule, whatever that means, right? But half a water molecule. So you're going to indicate the half with that prefix hemi. And you're going to indicate the water by using the word hydrate. So we have calcium sulfate, hemihydrate. All right. If you look at the last example on the page, COCl2.6H2O. Okay. You're going to say to yourself, all right, I'm going to name this first. I know that cobalt is a type 2 metal, so I'm going to indicate its charge, right? It must be a cobalt +2 ion because there's 2 chlorines attached to it. So that's cobalt 2 chloride. And then you're going to say there's 6 waters attached to it. So that's going to be hexahydrate. Right? So, you know, the hydrates work very similarly to the rest of the ionic compounds. The only difference is that you're literally going to add the number of waters that you're attaching to the end of the name. Okay. And don't confuse your hydration, your hydrated compounds with your molecular compounds. Even though we're using similar prefixes, hydrated compounds are still ionic compounds and they follow the rules of ionic compounds. We're going to switch now into the rules for naming molecular compounds, and we have to keep these clear in our head. Okay. The rules for naming molecular compounds are 100% different than naming ionic compounds. And that's why it's so important. That's why we spent so much time talking about what the difference is between molecular compounds. Because if you don't know what the difference between the 2 types of compounds are and how to tell, then naming them is going to be a big problem, right? So we are basically going to look at a compound, and if it consists only of nonmetals, that's how we will know it's a molecular compound. Okay? Molecular compounds don't combine based on charge the way ionic compounds do. That means that you can end up with, like this example shows you, 2 elements that have a huge variety of ways to combine. Okay, all of these are valid combinations of nitrogen and oxygen. And because they're not combining by charge, there's no format for it. There's no specific formula that it's following. So we're just going to name the molecular compounds based on the number of atoms of each element that make up that compound. All right? And we're going to do this using prefixes. You only use prefixes in molecular compounds. You will never use a prefix in an ionic compound. Okay? We are going to first write the name of the element that has the smallest group number, right? If 2 elements happen to be in the same group, you're going to write the one with the greatest row number first, and then the one with the smaller row number. And your prefixes are going to tell us how many atoms of each element are present in the particular compound that you're looking at. Okay, let's actually go back to this slide. Okay, now we have all these examples of these nitrogen and oxygen compounds. Let me write them down because we'll go through them. and we'll follow this process. Okay. Right, so based on the kind of rules that we were just talking about, and if you flip to the next slide, you'll see the actual format to use. Okay, we're going to look at the formula that we're given. Okay, we're going to look at the first element here, that's nitrogen. All right. Now, if there's only one atom of the first element, you don't have to write mono in front of it, okay? So we can like X that out. But you have to indicate exactly how many of the second element are attached. So instead of writing mono nitrogen, mono oxide, we could just write nitrogen mono oxide. And then you see how we have these repetition of the O there? We're going to combine that, and instead of the mono oxide, we're going to call it monoxide. Okay, so this would be nitrogen monoxide. Okay, again, we have one nitrogen to start with. Now we have two oxygens. So that will be dioxide. Now we have two nitrogens. So that's going to be dinitrogen. We have one oxygen, dinitrogen monoxide. Two nitrogens and three oxygens. Dinitrogen trioxide. Dinitrogen tetroxide. Dinitrogen pentoxide, or sometimes pentoxide, depending on how you read it. Okay, this is the formatting for your molecular compounds. This is the basic set of rules that are going to be followed. Now, just because we can leave this mono out of the first element in the formula of your molecular compounds, don't get that confused with your hydrated ionic compounds. All right, if you only have one water molecule attached to an ionic hydrated compound, you have to call that, you have to indicate that there is only one. That has to be monohydrate. Okay, just to keep that clear in your head. Okay, so these are the prefixes that we're going to use to indicate the number of atoms that are present. And we have some more examples here. Okay, so you can take a second, pause this, try them out if you haven't already. I'm going to click ahead. This should all make sense to you. You're going to notice that every element is represented kind of in the order that the formula is written. And the number of each atoms that are present in the formula are represented by these prefixes. Okay. Now, we looked at this conceptual connection in class. The compound NCl3 is nitrogen trichloride, but AlCl3 is simply aluminum chloride. And why is that? So the basis of answering this question is you being able to differentiate between a molecular compound and an ionic compound just looking at the formula. Okay? NCl3 is a molecular compound. There are no metals present. AlCl3 is an ionic compound. It's a metal and nonmetals. Now, when we have molecular compounds, that's when we're going to use prefixes like the mono, di, and tri. Molecular compounds only will have these types of prefixes. Ionic compounds are not going to. That's a big difference between them. Excuse me. Okay. Sorry, I need to pause that for a second and have a little coughing fit. But the last type of compound that we're going to look at now are going to be acids. Okay, and acids are a type of molecular compound, but we have to name them in a special way. Okay, so acids are going to be compounds that release hydrogen ions when they get dissolved in water. And acids are composed of hydrogen, and usually that hydrogen is going to be written in the front of the formula, and then the other nonmetals will be written in the second part of the formula. Okay, so we have an example here of HCl. HCl, when it's dissolved in water, is going to form hydrogen ions and chloride ions. This little AQ notation down here, that indicates the word aqueous, and aqueous means that it's dissolved in water. And here are some characteristics of the acids. They have a sour taste. They're able to dissolve many metals. You have that formula starting with the hydrogen, which is how you're going to be able to pick out that it's an acid, because it's going to have this H out front. And a substance can only be considered an acid if it is able to be dissolved in water. Okay. Oh, that was too fast. And there are two types of acids in particular that we're going to focus on. We have binary acids and oxyacids. Binary acids are going to have the hydrogen out front, and then they're going to be followed by a nonmetal that is not oxygen. Oxyacids, on the other hand, are going to have the hydrogen, and it's going to be followed by a polyatomic ion that does contain oxygen in it. So really, if you had a shorthand figure out what the difference is between a binary acid and an oxyacid has oxygen. A binary acid doesn't. I'm sorry, I'm gonna have to keep coughing like in your ears right now because my throat is like having a real itch in it. But we'll just ignore it. It'll go away eventually. Now we're going to look at how to name the binary acids first. You're going to follow the same formula every time. Okay, once you recognize that it's a binary acid, and you're going to know it's a binary acid because there will be no oxygen in it, you're going to start by writing the prefix hydro. Okay, you will only write the prefix hydro if it is a binary acid. After you write the prefix hydro, you're going to follow it with your non-metal base name. Then you're going to add an IC ending to that non-metal base name. And then you'll follow it with the word acid. Okay? For an oxyacid, the process is completely different. The entire name of the oxyacid is based on the name of the polyatomic ion that makes up the oxyacid. Okay, so you have to be able to recognize the polyatomic ion that makes up the oxyacid that you're looking at in order to be able to name the oxyacid. There are two types of polyatomic ions. One polyatomic ion type ends with an ATE. The other type ends with an ITE. Any polyatomic ion that ends with an ATE, that ATE ending is going to change to an IC ending. in its acid form. Any polyatomic ion that ends with an ITE, that ending will change to an OUS in its acid form. Okay? You will never write the prefix hydro in front of an oxyacid. Okay, it's based only on the polyatomic ion name and its new ending. So we are going to look at some examples for this, okay? So these three examples, we can look at this list really quickly and see that they're all binary acids, right? There's no oxygen involved. So we're going to start with the hydro prefix on all of them. Then we're going to take the root name of the anion and add the IC ending. So for HI, hydroiodic acid. For HF, hydrofluoric acid, hydrofluoric acid. For HBr, hydrobromic acid. You're going to notice up here that that combination happened. Instead of hydroiodic, it's hydroiodic, right? I'm writing it down in how it's commonly written so that when you see it, you won't be confused. You won't feel like I've never seen it that way before. It's just, it makes more sense when you're speaking it out to say hydroiodic acid, not hydroiodic acid. But it wouldn't be the end of the world if this is the thing that you forgot, okay? As long as you can recognize that this is the name that corresponds to this formula. Okay, now we're gonna try some with your oxyacids. Okay, we know that they're oxyacids. First of all, for our first three, we know these are oxyacids because we can like literally see these oxygens. We know that numbers 4 and 5 are oxyacids because they do not have hydro in the name. Okay. So we're going to do these ones on my whiteboard. So this first one, we have HC2, H3, O2. And we want to know what the name of this is. We see that it's an oxyacid. So right away we say to ourselves, we have to name this just based on the polyatomic ion that makes it up. So what is this polyatomic ion? This is the acetate ion. Okay, so if I have the acetate ion, I'm going to take this ATE ending, I'm going to erase it, and I'm going to replace the ATE with IC and add the word acid. So this is acetic acid. Okay. HNO2. What polyatomic ion is NO2 minus? It's the nitrite ion. So I'm going to take the ITE ending, get rid of it, and replace it with the OUS ending. Nitrous acid. HNO3. NO3 minus is the nitrate ion. I'm going to take the ATE ending and erase it and replace it with IC. Nitric acid. Okay? No hydro anywhere because they're all oxyacids and their name comes entirely from the polyatomic ion that makes them up. And we can go in the other direction as well. So for examples 4 and 5, we have perchloric acid and we have chloric acid. Okay, so to figure out what the what the formulas are going to be from the names, first we have to recognize what polyatomic ion this represents. So we know that if something has, so we have perchloric over here, okay? Change out markers. We know that this IC ending has replaced the ATE ending of our polyatomic ion. So now we know that this is the perchlorate ion. Okay, what is the perchlorate ion? It's ClO4 minus 1. So I'm going to need one hydrogen out front to counteract this -1 charge. So the formula for perchloric acid must be HClO4. Okay, do the same thing over here. If I have chloric acid, that means that I started with the chlorate ion. The chlorate ion is ClO3 minus 1. I need one hydrogen to counteract that -1 charge. So the formula for my chloric acid must be HClO3. All right. So hopefully that makes sense. All right, we have another set of examples that we'll go through. Okay, so take a look at this table. All right. I'm going to go back to my share screen and we'll go through these examples together. But you should be trying them out on your own. Okay, so the first one, we have nitrous acid. If we have nitrous acid, that means that we had an acid formed from the nitrite ion. The nitrite ion is NO2 minus 1. That means that the formula of the nitrous acid is going to be HNO2. Okay. If we have the formula NiIO3, what is this IO3? This is one of our oxyanions. It's IO3 minus 1. Okay, there are 2 of them. That means the total charge has to be -2. That means that this nickel has to be +2. Okay, so this is nickel 2 iodate, right? And this iodate works the same way as the chlorate did in our previous examples with the oxyanions. Okay. Next example, gold 3 sulfide. So we know we have Au3+ and S2-. That means that we're going to need 2 golds to balance the charge of 3 sulfurs, so that we have a +6 on the cation side and a -6 charge on the anion side. So our formula would be Au2S3. Okay. For the next example, we have H2SO3. This ion is the sulfite ion. I'm going to take this ITE ending, get rid of it. Okay, and I'm going to replace it with an OUS. Now, what we have here, we're going to star this one because we have a special exception. And there are only 2 exceptions with the oxy acids that you need to worry about. This is one of them. Instead of only using the polyatomic ion name, this particular acid kept the entire name of the first element that makes it up. So instead of being sulfous acid, it's sulfurous acid. Okay. And while we're speaking about this, we can mention the other example that's present, which we also mentioned in class, but it's always worth mentioning again. Okay, so if we have H2SO4, we run into the same situation. You know that this is the sulfate ion. You know that the ATE has to change into an IC. Okay, but we don't leave it as sulfic acid. We keep the whole name of the element that makes it up, sulfuric acid. These are the only two scenarios where you will run into this at this stage for this course. Okay, so just keep those two exceptions in your head. Okay, then we have nitrogen trifluoride. So that's going to be 1 nitrogen, 3 fluorines. All right, and we'll do one more set of examples. Share the screen again just so you can note these down. Okay, so the first one, we have sodium dichromate. We have to recognize the charges on both of them to form the formula, right? So we know that sodium has a +1 charge. And we know that the dichromate is Cr2O7, and then it's got a 2- charge. So I'm going to need 2 sodiums to counteract the charge of the dichromate. So the formula for that will be Na2Cr2O7. Okay. For Bri3, I'm going to recognize that that's a molecular compound. So I'm going to name it with prefixes. So I've got bromine. I don't have to write the mono out front. I can just write the bromine. And then there's 3 iodines. So that will be triiodide. Okay, the formula for copper 2 hypochlorite. First, I'm going to write out the charges for both of them. So I have copper 2. The hypochlorite oxyanion is going to be the least oxygenated of the series. So that will be ClO, only 1 oxygen, and then it has a -1 charge. So I'm going to need 2 of the hypochlorite ions to balance out the charge on the copper. So my formula will be CuClO2. Okay. For the next one, we have S2Cl2. That is a molecular compound, so I'm going to name it using prefixes. Disulfur, dichloride, and our last example, potassium nitride, is an ionic compound. So I have to make the formula based on the charges. So potassium is a +1 charge. Nitrogen is a -3 charge. I'll need 3 potassiums to balance out the charge of the nitrogen. So my formula will be K3N. Okay. So that's it for the naming. Hopefully this review will be helpful for you guys.